We will now study the Nernst equation. You have already studied this equation in the 12th standard. We consider a reversible cell reaction of the type A moles of A to plus B moles of B to give C moles of C plus D moles of D, where A, B, C, D is nothing but the number of moles of A, number of moles of B, number of moles of C, number of moles of D. So free energy change delta G for the above reversible reaction is given by Van 't Hoff's isotherm. Van 't Hoff isotherm is nothing but this particular equation, where delta G is the change in free energy or free energy change. Delta G naught is the standard free energy change. R is a gas constant. T is your temperature. Log of concentrate. When you write this A moles of A, C moles of C, you will write concentration of the reactant C raised to C moles, concentration of B raised to D moles, divided by concentration of A raised to A moles, concentration of B raised to B moles. Now standard free energy change and free energy change are also related to EMF of the cell by this equation. So you have to know the second equation now. Delta G is equal to minus NFE, where N is the number of electrons, F is the Faraday's, E is the EMF. So delta G is the free energy change is related to EMF of the cell. Similarly, standard free energy change is related to standard EMF of the cell. Now substituting the values of delta G and delta naught G, that these two equations, in the previous equation we get minus NFE. So instead of delta G, I will write minus NFE minus NFE naught plus RP log of C raised to C log of D raised to D divided by log of A raised to A into B raised to B. Our next step is divide this equation throughout by NF. So if you divide this equation by minus NF throughout, minus NF divided by minus NF, what happens is this minus NF will cancel out with minus NF. This will cancel out with this. Here it does not cancel out. So what remains here is E is equal to E naught. This is minus here, so this sign will change. It is minus RP upon NF log of concentration of C raised to C, concentration of D raised to D divided by concentration of A raised to A, concentration of B raised to B. So if we go to the next step, we have got that equation here. E is equal to E naught minus RP upon NF log of concentration of C raised to C, D raised to D divided by A raised to A, B raised to B. Now if you substitute the values of temperature. So this temperature we are going to substitute temperature is at 25 degrees centigrade. So if we want to convert it into degree Kelvin, 273.15 plus 25 degrees. So you have to substitute the temperature as 298.15 degree Kelvin, and you substitute the value of R. R is equal to 8.314 volt coulombs, and F you are going to substitute also. F is 96,500 coulombs, and N is nothing but the number of electrons involved in the reaction. So E is the EMF of the cell. So we write it as E of the cell is equal to E naught of the cell minus 0.059. How do we get this particular value? So we have the above equation, E is equal to E naught minus R value is 8.314 R into T. Temperature is 298.15 divided by N. Since we have taken a general equation, we don't know the value of N. We write N as it is. Faradays is 96,500 Faradays. And if you want to convert your log ln is equal to log to the base 10, you have to multiply by 2.303. So here we multiply this by we multiply this by 2.303 and convert this into log. So convert this log ln into log to the base 10. We have log of C raised to C log of concentration B raised to D divided by concentration of A raised to A, concentration of B raised to B. Okay, now to get this value, what we have to do is we multiply all these numericals. So when we multiply and divide by 96,500, I get the value 0.059 divided by N, and log of concentration of C raised to C, C raised to C into D raised to D divided by A raised to A, B raised to B. So you will get this particular equation. EMF of the cell is equal to E naught of the cell minus 0.0591 into, this is multiplied into log of this. Okay, now when will E be equal to E naught of the cell? When will E be equal to E naught of the cell? E will be equal to E naught of the cell when this full term will be equal to 0. And when will this full term be equal to 0? When log this term becomes 1. That is what? When all the concentration terms are equal to 1. Concentration of C is equal to 1, concentration of D is equal to 1, concentration of A is equal to 1, and concentration of B is equal to 1. So all the species involved in the reversible cell reaction are in their standard state of unit activity. That is, activity of all this C is equal to 1, activity of D is equal to 1. It means the same thing, that is, the concentration is equal to 1. So when they are in their unit activity, state of unit activity, that is when their concentrations is equal to 1, this will become log of 1. So log of 1 is nothing but equal to 0. So this full term becomes equal to 0, and this also multiplied by this will be 0. So E, that is EMF of the cell, becomes equal to the standard EMF of the cell when all the species involved in the reversible cell reaction are in their standard state of unit activity. So how do we define standard EMF of the cell? You have to define standard EMF of the cell. So standard EMF of the cell can be defined as EMF of the cell. Okay, standard EMF is nothing but EMF of the cell when all the species involved in the reversible cell reaction are in their standard state of unit activity. What do we mean by species involved? All the reactants and the products. So that is how we define standard EMF of the cell. Now, in general, an electrochemical reaction is represented as, we write the reduced state to give us the oxidized state plus n number of electrons. So when we have a reaction like this, we can write a reduced state is equal to oxidized state. This is an arrow, oxidized state plus n number of electrons. So EMF, the Nernst equation, can be written as E is equal to E naught minus 0.059 divided by n log of, it is activity of the oxidized state here divided by activity of the reduced state. You can write also E is equal to E naught minus 0.059 upon n log of concentration, activity of the products divided by activity of the reactants. Okay, so here these are your reactants and this is oxidized state is your products. So using this you can write for any cell, you can write for any electrode also. So a derivation of the Nernst equation for single electrode potential. Now the same procedure as you have done for the derivation of the Nernst equation for a cell, okay, where we have started with the standard free energy change. So from there onwards you have to start the derivation plus RT upon NF log of, we had written concentration of the products divided by concentration of the reactant. So here in this case, when we are talking about a single electrode, it can be any electrode because we have studied the different types of electrode. You have to remember all the different types of electrode. You have to remember their cell reaction and you have to remember their representation. So if I take the first electrode, say the metal ion electrode, so this is the oxidation reaction. Okay, this is the oxidation reaction of that particular electrode, metal, to give us metal ions plus n number of electrons. Now it can be any metal. For example, here I have taken copper. So if you are writing the copper reaction, copper will give you Cu plus 2 electrons. So if this is your oxidation reaction, okay, so here while writing, how will you write? Log of concentration of the product. So it is concentration of Cu plus 2 divided by concentration of the reactants. And then you continue with the derivation. You know delta G is equal to minus NFE, and you have delta G naught is equal to minus NFE naught. So substitute these two equations in the above equation, and then you have E is equal to E naught minus RT upon NF. All after substituting those values also, we get 0.059 divided by N log of concentration of the copper ions divided by concentration of copper. Number of electrons involved in this reaction is 2. So you will write this N as equal to 2. Concentration of copper is usually given when you are solving the problems. Now, concentration of the pure metal is equal to 1, is taken as 1. Concentration of any pure metal in the solid state is taken as 1. So this is your Nernst equation for single electrode potential, which you have derived in a similar way how you have derived for the cell reaction. Now this is for the metal ion electrode. You can have any other type of electrode. Now here we have taken the redox electrode. So this is nothing but another type of electrode, the redox electrode, where the reduction and oxidation species this is the reduction electrode, I said. Redox electrode. So we have the reduction and oxidation species present in the same electrode, where Fe plus 2 is the reduced species and Fe plus 3 is your oxidized species. Okay. So if you consider the oxidation reaction, then it will be Fe plus 2 to give you Fe plus 3 plus an electron. Okay, so even the charges have to be balanced. It is plus 2 and it is plus 3 minus 1. So this plus 2 plus 2 plus 2, the charges get balanced. So if this is the oxidation reaction, number of electrons involved is 1, then you can write your Nernst equation, you can write the derivation for the same and arrive at this particular equation. E is equal to E naught minus 0.059 divided by n, and is found here, log of concentration of Fe plus 3 divided by concentration of Fe plus 2. So this is your reactants and these are your products. Okay, so when you write, it is always log of concentration of the products divided by concentration of the reactant. Now this is your oxidation reaction. Suppose you are writing your reduction reaction, then what will happen is, if you are writing the reduction reaction, it is Fe plus 3 plus an electron to give you Fe plus 2, which is the opposite reaction. So in such a case, what will be your Nernst equation? Your Nernst equation will be E is equal to E naught minus 0.059 divided by 1. This will be log of concentration of your products, that is Fe plus 2 divided by concentration of Fe plus 3. So you have to write always concentration of the products divided by concentration of the reactant, depending upon what type of reaction. Now, the next thing is, if you have understood whatever we have done till now, from the first lecture, second lecture, and today's lecture I have divided it into parts so that you get smaller videos which you can open up faster. So some questions there is, what is EMF? What are the different types of electrodes? Write the representation in the cell reaction of the calomel electrode. Explain the linear cell. What is the salt bridge and what is its function? What are reversible and irreversible cells? Explain the hydrogen gas electrode. What are the advantages and disadvantages of the hydrogen gas electrode? Explain the conventional representation of the electrolytic cell. Give an example of a redox electrode and explain the calomel electrode. What are the disadvantages of the two-motor electrode, etc., etc. Various questions can be asked, and if you can answer all these questions, then you have understood whatever we have done so far. Our next lecture would be on problems. I will solve some problems and will upload a video one of these days, and then you can solve the remaining problems based on similar explanation, and you can go ahead with the next part. Thank you.